Hi everyone. So, in case Ms. Monterano hasn't told you guys yet, you're not allowed to use a calculator on the multiple choice of the AP Chemistry exam, which may be hard to put into perspective now, considering we do use calculators pretty often and on every test. But it's not too bad when you break down the fact that the AP test cannot give you questions that you can't do without a calculator. So, I hope that throughout this video, we pick up on some simple rules that will help us not only now but through the AP exam. So first things first, we're just going to start off with some simple math rules. And to begin, we have to know that when you divide exponents of the same base, you get that base to those exponents subtracted. Or in other words, if you have x to the 4th divided by x to the 3rd, for example, you're getting x to the 4 minus 3 or x to the 1st. Now, using a variable like this is kind of hard to put into perspective, and so we're going to use it in numerical form now. For example, 0.00005 divided by 0.09. And now you might be thinking, how do I know that these are or these aren't of the same base? We're going to act as if this one right here, this right here, is 10, about 10 to the negative 1, 2, 3, because this is going to round up. And then this one is 10 to the negative 1, because this one rounds up. That's why this rule also works with this. So what we first want to do is cancel the zeros. As if we were in any algebra class, they would tell you that if you have zeros on top and zeros on bottom, you want to cancel those zeros. That leaves you with 3 zeros. Don't forget your decimal place is still here. 3 zeros, but then we still have 5 divided by 9. Now, 5 divided by 9, the 9 series is 1 divided by 9 is 0.11111. 2 divided by 9 is 0.22222. 3 divided by 9 is 0.33333, in case you didn't know this. So 5 divided by 9 is going to be 0.55555, repeating, or in other words, 0.56. Because we have that 0.56, we add an extra 0. That's why instead of 3, we have 4. And we get 56 because we had 0.56. So that is our estimated answer for that. Another rule here is that if you multiply exponents of the same base, you get that base to the exponents added. In variable form, this is simply x to the 4th, for example, times x to the 3rd is the same thing as x to the 4 plus 3, or x to the 7th. Let's do a numerical example like last time. 0.0004 times 0.006. Now, we're adding, so we're going to add our zeros. 1, 2, 3, 4, 5 after the decimal place. And we get 0.1234 zeros, just because we had 5 zeros here. And then 4 times 6, which is 24. Next, we're simply going to go over a few chemistry facts and equations that we're going to be using with our simple math rules. The first that we have is pH is equal to the negative log of the concentration of hydrogen ions. Generally, we know that the P of anything is equal to the negative log of anything. So we also know that the P of hydroxide is equal to the negative log of hydroxide. Another rule that we have is that the pH plus the pOH is always equal to 14. They must always add up to 14. Additionally, we have inverse log, and we know that 10 to the log, base 10, cancels out and equals 1, because these right here are inverses of each other. Log is log base 10, ln 10, and then 10 cancels out with that, making just 1. Additionally, log of 10 is equal to 1 for the same reason. These are inverse functions. So, for example, if we're giving this right here, which would be an equation like this, we would bring this 5 as a coefficient. It comes down, and then log of 10, as we see here, just equals 1. So we're going to get 5 times 1, which is simply equal to 5. Our first example is asking, how do we calculate the approximate pH of a solution that has a hydrogen concentration of 0.00065 molar? And as we look at this problem, we have to think to ourselves, it says approximate right here, approximate pH. It's not looking for a definite answer, one, and it's asking for concentration via molarity. So we know that we have to use the pH is equal to the negative log of hydroxide ions. But first, or hydrogen ions, I should say. But the first thing we want to do is round this concentration to a factor of 10 so that it's easier to use in the equation itself. This is going to round up, so it's going to be 0.001 as indicated here. And the next thing we want to do is change this to scientific notation, and this is going to be the same as 10 to the negative third. Now we want to be able to plug into this equation that we have, pH is equal to the negative log of hydrogen ions, and what we get is 3, because this negative 3 comes down as a coefficient, the negatives cancel, and you're left with 3 log of 10, which of course we know log of 10 is equal to just 1, and we're left with 3. Our next example asks, how do we calculate the approximate hydrogen concentration of a solution that has a pH of 4? So now we're working in the opposite direction. We're starting with a pH and we're solving for concentration. Again, we're going to use our pH is equal to the negative log of hydrogen ion equation, but now we're plugging in 4 for pH. Our next step is to solve for x using the inverse properties that we know. And we're basically going to do what we would do in algebra and isolate the x, and first we divide by negative 1, giving us negative 4 is equal to the log of x. Then using inverse properties, we're going to take 10, both sides to 10, this is worded weird, but you want a base of 10 and then both sides to a power. So we're going to have 10 to the negative 4 is equal to 10 to the log of x. As we know, 10 to the log, which is log base 10, are going to cancel and equal 1, and this x is going to come down, and simply x is equal to 10 to the negative 4. And unfortunately, the examples I just showed you are pretty easy, and the AP test isn't actually going to be like that. So for the next few examples, we're going to do real AP test application. The first question asks, what is the concentration of potassium chloride in a solution made by mixing 10 milliliters of 0.1 molar potassium chloride with 50 milliliters of 0.1 molar potassium chloride? So basically, we're just mixing different volumes of the same substance. And the first thing that we want to do is use our mole is equal to molarity times volume equation, because what our knowns are volume and molarity. And we're going to switch over the volumes to liters because that's what the equations ask for. So we're going to have 0.050 liters times 0.1 molar. And like we learned before, we're just going to add the zeros. So 1, 2, 3, 0.005, because 5 times 1, 0 moles. 1, 2, 3, 1, 2, 3. We're going to do it for the other sample of the substance. So we have 0.010 liters, or 10 milliliters, times 0.1 molar, or 0.100 molar in this case. And again, we're going to add these zeros, 1, 2, 3. And 1 times 1 is simply 1. There are 2 moles. The next thing we're going to do is find the additive volume. So the 2 different samples we have of different volumes, we're simply going to add them together. We have 0.010 liters plus 0.050 liters. Simply add these as if they were one top of another, if you want to picture it that way. But it's just, I think that's pretty simple math. I think you guys know how to do that one. And now the next thing we want to do is solve for final concentration using our expression moles equal to molarity times liters, or we could change this around to make it molarities equal to moles over volume. We're going to plug in for our total moles, which we solved for over here, 0.0010 moles. Oh, yes. We're going to add our moles first. Sorry, we skipped that step. So what we want to do is add these together, and we get 0.00, hi Leanne, hello, 0.0060 moles over 0.060 liters. And we're simply going to cross out the zeros like we also learned before, leaving us with 0.0 yes, 0.10. And that's our final, 10, 0.10. Our next example asks us to consider 100 milliliters of 0.01 molar solution of sodium hydroxide. It also asks us to calculate the pH of the solution after 900 milliliters of distilled water are added to the solution. Because we're adding distilled water, this indicates to use the dilution equation, which is simply M1V1 is equal to M2V2. This helps us solve for the diluted molarity after the volumes are added. So to use the equation, we're simply going to add what we know, plug in what we know, which is the original molarity, concentration, which is 0.01 molar, the original volume, which is 100 milliliters, and then the additive volume of the two, 100 milliliters and 900 milliliters, adding up to 1,000 milliliters in order to solve for M2. We're then going to transform the equation in order to make it equal M2, and then we're going to use the math rules we just learned and cross out some zeros in order to divide. That leaves us with 0.01 times 1 over 10. Again, we want to use the math rules we just learned. We're going to pretend that this 10 on the bottom is like a 10.0, leaving us with 0.001, 3 zeros, concentration of NaOH. We're then going to convert that to scientific notation in order to make this easier to solve the pH. So 0.001 is the same thing as 10 to the negative third. We're then going to plug this concentration into the pH. P of OH is equal to the negative log of the concentration of hydroxide ions. Simply plug again what we know. Negative log of the concentration of OH ions is 10 to the negative third. And then we're going to solve by bringing this negative 3 down. This cancels with the negative, leaving 3 log of 10, which we then know is simply equal to 3. We're then going to use our next rule to solve for pH, which is pH plus POH is always equal to 14. We're then going to subtract 3 from 14 and get a pH of 11. And that is our answer. This example problem asks, what are the respective concentrations of sodium and sulfate ions afforded by dissolving 0.5 moles of sodium sulfate in water and diluting to 1.33 liters? You may look at this problem on the AP test and think, oh my god, how the heck do I do this without using a calculator? Look at the answer choices. These are unreasonable numbers, and I can't solve for every possible outcome. And that right there should be an indication that you do not solve this using unreasonable math, and that there must be some way to break down the answer choices and use them to your advantage to find what the right answer is. So the first thing we're going to do is consider the chemical formula, which is Na2SO4, or in other words, for every one sulfate ion there is, for every one sulfate, there's 2 sodium. So if we look at our answer choices, the only real options here are A and C, because these answer choices, as it says, are in respective concentrations, and that means that the sodium has to be double that of sulfate, and therefore the only answer choices that are in a 2-to-1 ratio are A and C. This number times 2 is this, and this number times 2 is this. The next step of this problem is to consider what the question is actually providing us with, I should say, and that is volume and moles. And the first thing that should come to your mind is that concentration is equal to moles over liters, because that is what we are given. So let's say we want to solve for the concentration of sodium and just give it a shot here. So the moles of sodium, if we are given 0.5 moles of sodium sulfate, for every 1 mole of that, there's 2 moles of sodium. So we're going to have 1 total mole of sodium, because double of 0.5, over what the volume we are given, which is 1.3 or 1.33. And we're just going to solve and find that 1 is the same thing as 1 over 1. 1.3 is the same thing as 4/3. Do a same change flip and get that the concentration is equal to 3/4 or 0.75. The answer choice that matches that for concentration of sodium is most obviously A. And just simply by plugging in and solving for A, we could see that A is the right answer. It helped that we were able to break down these answer choices, and we are left with concluding that the answer is in fact A. That concludes my video on how to do some simple math tricks, some simple chemistry equations to your advantage when it comes to without using a calculator on the AP exam.